Hello, good morning. Hello.
Human share में
Okay, good morning. Welcome back to the contributory session. So in this session, we have 5 speakers. The first speaker is Shivani Rai from Sikkim Manipal Institute of Technology, presenting on properties of some neighborhood degree-based topological indices of graphs. The second speaker is Aniruddha Samanta from Indian Institute of Technology, Kharagpur, presenting on gain distance matrices for complex unit gain graphs. The third speaker is Kuldeep Sarma from Tezpur University, presenting on inverses of non-bipartite uncyclic graphs with a unique perfect matching. The fourth speaker is Suman Maiti from National Institute of Technology, Roorkela, presenting on interval eigenvalue problems and its applications. The final speaker is Yogesh Kumar Prajapati from Indian Institute of Science and Education, Thiruvananthapuram, presenting on dynamics of non-negative matrices. So I request Professor Arati Bhatt, Manipal Institute of Technology, to chair this session. Over to you, ma'am.
Thank you, Raksha. We'll begin the session. First presentation is by Shivani Rai from Sikkim Manipal Institute of Technology. Title of the talk is on properties of some neighborhood degree-based topological indices of graphs.
Hello everyone, my name is Shivani Rai and I'm a research scholar under the supervision of Dr. Biswajit Deb, Department of Mathematics, Sikkim Manipal Institute of Technology, Majidar, Sikkim. The topic for my talk today is on properties of some neighborhood degree-based topological indices of graphs. This is the outline of my talk. So moving on with the background. With the rapid advancement of medication, nanotechnology, bioinformatics, and cheminformatics, there is an increased expense to acquire equipment and reagents to test the properties, activity, and toxicity of new drugs and chemical compounds. So the use of topological indices is an efficient alternative to predict their properties without the use of lab. And the indices encode the structure of various chemical compounds in the form of real numbers. Thereby, the analysis of various compounds can be done effectively with less cost. Also, there are several software that provide algorithms to simplify the computation of these indices. For the introduction, what is a topological index? So a numerical parameter associated with molecular graphs of chemical compounds is termed as a topological index. And by a molecular graph of chemical compounds, we mean a structural representation of a chemical compound, wherein the atoms are represented by the vertices of the graph, and the bonds between them are represented by the edges joining the vertices of the graph. A topological index is highly correlated with the topology or the branching pattern of a network, and it helps in the characterization and analysis of various structures. Also, it is a useful tool in the quantitative structure-property relationship and quantitative structure-activity relationship studies, as it gives insight into the physical and the chemical properties of any chemical compound. Now, the classification of topological indices can be done broadly under the 3 heads. Firstly, we have the distance-based topological indices. As the name suggests, these indices are based on the distance between the vertices of the graph. Example, the Wiener index, the Harari index, etc. Secondly, the degree-based topological indices and their neighborhood degree sum-based versions. As the name suggests, these indices are based on the degrees of the vertices of the graph and their neighborhood degree sum, which we'll be discussing about in a short while. Examples include the Zagreb indices, that's the first Zagreb index of G, M1G, and the second Zagreb index, M2 of G, and the geometric arithmetic index and their neighborhood versions, etc. And the final one, we have the spectral-based topological indices, and these are based on the spectrum or the eigenvalues of the Laplacian or the adjacency matrices of the graph. Examples, the graph energy, quasi-Wiener index, etc. Now, some neighborhood degree-based topological indices. These are based on the neighborhood degree sum of the vertices of the graph. And by neighborhood degree sum of the vertices, we mean the sum of degrees of the vertices adjacent to a vertex V. And it is denoted by delta of V. So one of the neighborhood degree-based topological index, that is the neighborhood general first Algebra index of a graph G, is defined as the summation of the eighth power of delta of U, where U belongs to the vertex set of G. And when we assign various values to A, we get different neighborhood-based topological indices. That is, when A is equal to 2, minus 1, and minus half, the indices so obtained are the neighborhood first Algebra index, the neighborhood modified first Algebra index, neighborhood inverse degree index, and neighborhood zeroth order index, respectively. Furthermore, in 2019, Cully proposed the neighborhood version of the general first Algebra index, the modified first neighborhood index, neighborhood inverse degree index, neighborhood zeroth order index, and computed it for the line graph of subdivision graphs of CU, C4, C8. Also, the fifth geometric arithmetic index, GA5, was introduced by A. Grauwach and his co-authors in 2011, and it was computed for nanostar dendrimers. So therefore, with the introduction of every new topological index, the study of these indices for various compounds and nanomaterials has been an active area of research. So the aforementioned indices are defined as follows. The modified first neighborhood index is equal to the summation of 1 by square of the delta of U, where U belongs to the vertex set of G. The neighborhood inverse degree index, which is denoted by NID of G, is equal to the summation of 1 by delta of U, where U belongs to the vertex set of G. The neighborhood inverse degree index, which is denoted by the neighborhood zeroth order index, which is denoted by n set of G, which is equal to the summation of 1 by square root of delta of U, and U belongs to the vertex set of G. And the fifth geometric arithmetic index, which is denoted by GA5 of G, is equal to the summation of 2 times the square root of delta of U into delta of V, divided by the sum of delta of U and delta of V, where UV belongs to the edge set of G. Now, for the chemical significance of these four indices, when we consider the case of the benchmark data set of octane isomers, which are 18 in number, when the models of two indices were taken simultaneously, then it was seen to show remarkable correlation with properties like entropy, standard enthalpy of vaporization, and eccentric factor, as compared to taking the individual indices for consideration. On the other hand, individually, all the four indices can efficiently model the pi electron energy and boiling point for the set of 30 benzenoid hydrocarbons as well. And by efficiently model, we mean that the correlation coefficient between these indices and the properties is greater than 0.8. One of the most crucial criteria for a topological index, that is isomer discrimination ability, is also inferred to outmatch the existing degree-based indices. So by an isomer discrimination ability of a topological index, we mean that the topological index gives distinct values to the isomers of the data set. Moving on with the main results. So here we'll be discussing on the bounds of these four indices in terms of various graph invariants. So for the first theorem, we have if G is a non-regular graph without isolated vertices with n greater than or equal to 3, then the modified neighborhood first Algebra index has a lower bound as shown. And at this juncture, I would like to state that when the neighborhood degree sum of the vertices are arranged in non-increasing order, such that delta of 1 is the highest value of the neighborhood degree sum of the vertices and delta of n is the lowest value of the neighborhood degree sum of the vertices, then equality in this case holds if and only if the neighborhood degree sum of the vertices can be partitioned into two sets, the greater one being n minus 1 times delta minus 2. For example, When we remove an edge from a complete graph on n vertices, then the condition is satisfied and the lower bound for this index is achieved. Similarly, here we have the upper bound for the modified neighborhood first algorithm index. And here too, the equality holds if and only if the neighborhood degree sum of the vertices are partitioned into two sets, but here the lesser one being delta plus 1. For example, when we consider a link of Kn and an isolated vertex V, that is when we append an isolated vertex to any of the vertices of a complete graph on n vertices, the condition is satisfied and the upper bound for this index is achieved. Next, if G is a graph without isolated vertices with order n greater than or equal to 3, then the lower bound for the modified neighborhood first algorithm index of G is obtained as shown here. And the extremal case is when the delta of 2 is equal to delta of 3 and so on is equal to delta of n minus 1. As an example, we have a graph G is equal to the path on n vertices. The condition is satisfied and the upper bound for this index is achieved. Now, this is again a lower bound for the modified neighborhood first algorithm index of G. In terms of the neighborhood inverse degree index of G and the first algorithm index, that is a degree-based topological index of the graph. And here equality holds if and only if delta of U is equal to n minus 1 times delta minus 2 for every vertex U belonging to V of G. Now moving on with the bounds of the neighborhood inverse degree index of a graph. If G is a non-trivial graph with n vertices, then the upper bound for the neighborhood inverse degree index of G is equal to n minus 1 times delta times the modified neighborhood first algorithm index of G. And the extremal case is when the graph G is equal to the complete graph on n vertices. Next, if G is a non-trivial graph, then the lower bound for the inverse degree index of G is given as shown here, which is delta plus 1 times the modified neighborhood inverse degree index of a graph G. The modified neighborhood first algorithm index of graph G, and equality holds if and only if delta of U is equal to delta plus 1 for every U belonging to the vertex set of G. If G is a non-trivial graph, then the neighborhood inverse degree index of G is greater than or equal to n squared by the first algorithm index of G. And equality holds if and only if delta of U is equal to delta of V for every pair of vertices U of V belonging to V of G. So this is an upper bound for the neighborhood inverse degree index of G. When G is a non-trivial graph, then you can see the upper bound here. So an equality holds if and only if G is regular. Going ahead with the bounds of the neighborhood zeroth order index of the graph G. If G is a non-trivial graph, then n0 of G is greater than or equal to 1 by the maximum degree cube times the first algorithm index of a graph G, and equality holds if and only if G is regular. Let G be a non-trivial graph, then the lower bound for the neighborhood zeroth order index of graph G in terms of the number of vertices of the graph and the first algorithm index of G is given as shown here. And equality holds if and only if delta of U is equal to 1 for every V or for every U, and when G is a union of K2 or pairwise disjoint edges. If G is a non-trivial graph, then n0 of G is less than or equal to the square root of n times nid of G, and equality holds if and only if delta of U is equal to delta of V for every U, V belonging to the vertex set of G. Next, if G is a non-trivial graph, then n0 of G is greater than or equal to 2 times the minimum degree times the maximum degree, square root of n times nid of G, divided by the square of the minimum degree plus the square of the maximum degree, and equality holds if and only if G is a union of K2. Now, finally, we have the bounds for the fifth geometric arithmetic index If G is a simple graph without isolated vertices and m number of edges, then the fifth geometric arithmetic index is always less than equal to m. And equality holds if and only if G is the union of K2. Another upper bound for the fifth geometric arithmetic index is M2 of G, where M2 of G is the second Zagreb index, which we have already mentioned. And equality holds if and only if G is a union of pairwise disjoint edges. Last but not the least, if G is a simple graph without isolated vertices, then the fifth geometric arithmetic index is always less than equal to the square root of m times the neighborhood second Zagreb index of G. And here the extremal case is when G is a union of pairwise disjoint edges. Finally, if G is a simple graph without isolated vertices, then the lower bound of GA5 is given by this expression. And equality holds if and only if G is a union of K2. So now to summarize my talk, the upper and lower bounds of some neighborhood degree-based topological indices have been determined in terms of graph invariance, like the number of vertices and edges, minimum and maximum degrees of a graph. And we've also seen the relation between different neighborhood degree-based vertices and degree-based indices. The extremal graphs with respect to these indices have been characterized. Also, the investigation of these indices is under progress for various nanomaterials and polycyclic aromatic compounds. So these are my references. And this brings me to the end of my presentation. Thank you.
Any questions from audience?
Any questions from audience? No questions, ma'am.
Okay, then we thank Shivani Rai. So we'll continue with the next talk. It's by Aniruddha Samant from IIT Kharagpur. Title of the presentation is Gain Distance Matrices for Complex Unit Gain Graphs.
Myself, Aniruddha Samanto. I am a research scholar in the Department of Mathematics, Indian Institute of Technology, Kharagpur, under the supervisions of Dr. M. Rajesh Kannan. First of all, I would like to thank the organizer for giving me the opportunity to present my work here. Today, I am going to deliver a talk on gain distance matrices for complex unit gain graphs. This is a joint work with my supervisor, Dr. M. Rajesh Kannan. Now, our broad research area is spectral graph theory. As we know that in spectral graph theory, we mostly deal with the properties of graphs in terms of their associated matrix properties and vice versa. There are different kinds of matrices can be associated with a graph like adjacency matrix, incidence matrix, distance matrix, etc. Among such matrices, the distance matrix of an undirected graph is a well-known class of matrices in spectral graph theory. Now, instead of considering undirected graph, here we will consider a new bigger class of graph, namely complex unit gain graphs or T-gain graphs. T-gain graphs can be thought of as a generalizations of undirected graph, sign graph, width graph, oriented graph, digraph, etc. So here our main aim is to develop the notion of distance matrices for T-gain graphs and study their properties. Now, what is T-gain graph? The concept of T-gain graph mainly came from the concept of G-gain graph or simply gain graph. Jaslovsky introduced the concept of G-gain graph in 1989, where G is a multiplicative group. Consider G is any simple graph with vertex set V of G is equal to V1, V2 up to Vn and edge set E of G. Now an undirected edge between the vertices Vi and Vj is denoted by Ei, j, and an oriented edge from the vertex Vi to Vj is denoted by Eij arrow. Then each undirected edge can be considered as a pair of oriented edges. One is from Vi to Vj, another is from Vj to Vi. So now the collections of all such pair of oriented edges is known as directed edge set of G, and it is denoted by E arrow G. Now a G gain graph on a simple graph G is a graph such that if an oriented edge, let's say Ei, j, assign a value small s coming from the multiplicative group G, then the value of the reverse oriented edge Ji is S inverse, which is the multiplicative inverse of S. Let us call this assignment by phi, and this is known as the gain function. So gain function phi, this is a mapping from directed edge set to multiplicative group G. Later in 2011, Rev considered a particular choice of G. He assumed G to be a unit circle and put forward the concept of T gain graph. So a complex unit gain graph or T gain graph on an underlying graph G together with a gain function phi is simply denoted by capital Phi, and this is G, phi. Now some of the basic definitions. So the gain of a cycle C is nothing but the product of the gain of the oriented edges in this cycle. A cycle C is said to be neutral if its gain is 1, and a gain graph is said to be balanced if its all cycles are neutral. A switching function is a function from vertex set of G to unit circle. Two T gain graph phi 1 and phi 2 are switching equivalent, and they are denoted by phi 1 is switching equivalent to phi 2 if there is a switching function zeta such that phi 1 can be written in terms of the switching function zeta. So phi 1 can be switches to phi 2 through a switching function zeta. So the adjacency matrix of a T gain graph defined canonically. So the adjacency matrix of a T gain graph, this is a Hermitian matrix, and its ijth entry is the gain of the oriented edges from the vertex Vi to Vj and 0 otherwise. So one example, so this is the underlining graph and this is one T gain graph. So in this T gain graph, we can see that in this orientation, the gain is I. Therefore, the reverse orientation, the gain will be I inverse, that is minus I. So in this way, if we change the gain of its edges, we have different T gain graphs. So here we have phi 2, different T gain graph. In this way, we have uncountable many T gain graph associated with a particular structure G. So these are the adjacency matrices of phi 1 and phi 2. So here we can see that it's 1, 2 entries, that is 1 to 2, its gain is I, therefore this entry is I over here. Now some of the notation. So let phi be a connected T gain graph. Let S and T be two vertices of V of G. Consider SPT as an oriented path from the vertex S to T. Now define TST. This is the collections of all shortest oriented path from S to T. T mean ST. This is the collections of all shortest oriented path from S to T, such that the real part of gain of SPT is minimum over the real part of gain of all shortest path from S to T. Similarly, T max S, T. So now we denote a ordered vertex set V of G together with a ordering. So here less, this is a total ordering of the vertices of G. Let V of G, this is a vertex set V1 up to Vn, and an ordering less R is the reverse ordering of less if Vi less R Vj, if and only if Vj less Vi for all the vertices Vi and Vj. Now an ordering less is the standard vertex ordering if their vertices obey this total ordering V1 less than V2 up to less than Vn. Now we define two auxiliary gain functions. One is maximum auxiliary gain function, another is minimum auxiliary gain function. So let phi be a connected T gain graph, and let this is a vertex ordering on the vertices of G. Then two auxiliary gain function. One is maximum auxiliary gain functions with respect to the vertex ordering list. This is a mapping phi max less v cross v to t defined as follows. So phi max less over all the vertices s comma s is 0, and suppose two vertices s and t such that s less than t, then phi max less ht, this is the gain of the shortest oriented path from s to t, spt, where spt coming from p max ht and its imaginary part is maximum. And in that time, phi max less ts, this is the complex conjugate of phi max less st. Similarly, we can define the minimum auxiliary gain function. Now, on the other hand, we can define maximum and minimum auxiliary gain function through lexicographic ordering of complex number. So suppose s and t be two vertices and s less than t. So then phi max less st, this is the maximum gain over all shortest path from s to t. And this is the minimum gain over all shortest path from s to t. Here maximum and minimum are taken with respect to lexicographic ordering of complex number. Now gain distances. So let phi be a connected t-gain graph with vertex ordering less. Then we can define two gain distances. One is max, another is mean with respect to less. So then d max less st, this is the product of the auxiliary gain times the distance between s and t. Similarly for minimum. Now the gain distance matrices. So let phi be a connected t-gain graph with a vertex ordering less. Then we can define two distance matrices. One is max, another is mean with respect to the vertex ordering less. So they are the Hermitian matrices and their ijth entries. In case of the maximum, their ijth entries will be the d max less vi comma vj, and similarly for minimum. So one example. So let phi be a connected t-gain graph, and here we are taking the vertex ordering as standard vertex ordering. Then our d max phi will be this. So here we can see that, for an example, 3,5 entries. So that means from v3 to v5 we have two shortest paths. So now we calculate maximum of them with lexicographic ordering. Then we can get these entries 3 times e to the power iota pi by 6 and so on. Similarly, we have d max with respect to the reverse ordering of the standard vertex ordering. So here we can observe that d max are different with respect to standard vertex ordering and the reverse of the standard vertex ordering. In fact, their spectrum are also different. Now vertex ordering independent, let phi be a t-gain graph, and then this phi is vertex ordering independent if d max are same with respect to standard and the reverse vertex ordering, and d min are same with respect to standard and the reverse vertex ordering. In that time, their common value is denoted by d max phi and their common value is denoted by d min phi. Now this is the characterizations for ordering independent t-gain graph. Let phi be a t-gain graph, then phi is not ordering independent if and only if at least one of the following holds. There exist two vertices s and t with at least two shortest paths from s to t in p max st having different gain. And also there exist two vertices s and t with at least two shortest paths from s to t in p min st having different gain. Let phi be a t-gain graph, and let less a be the standard and the arbitrary vertex ordering on D of G. Then d max and d min are same with respect to standard vertex ordering if and only if d max and d min are same with respect to any arbitrary vertex ordering. Now gain distance compatible t-gain graph, or simply distance compatible t-gain graph. So let phi be a t-gain graph, then this is a gain distance compatible t-gain graph or distance compatible t-gain graph if their distance, if d max and d min are same with respect to standard vertex ordering. And in this case, we define their common value by d of phi, which is the distance matrix of a t-gain graph phi. Let phi be any distance compatible T-gain graph and phi switching equivalent to psi. Then psi is distance compatible. Also, the spectra of that distance matrices are same. Now we define positively weighted T-gain graph. So a positively weighted T-gain graph is a graph together with a weighted gain function. So that weighted gain function is nothing but the product of the gain times the weight of the edge. And it is denoted by G, phi, W, or simply phi W. Now, one of our main result in this section, let phi W be a positively weighted T-gain graph, then phi W and GW are co-spectral if and only phi is balanced. Now, using this result, we can deduce many known results. Some of them are, so first one is Acharya's fractal criteria. Let phi be a sine graph. Then the spectra of, let phi be a sine graph. Then the spectra of psi and G coincide if and only if psi is balanced. So another is about sine graph also. Let phi be a sine graph and W be a positively weighted function. Then phi W and GW are co-spectral if and only if psi is balanced. Another main result in this section, let phi W be a connected positively weighted T-gain graph, then the spectral radii of phi W and GW are equal if and only if either phi or minus phi is balanced. Some of the consequences of this result. So first one is, let phi W be a connected positively weighted T-gain graph, then the largest eigenvalue of phi W and GW are equal if and only phi is balanced. The next one is, let phi be a connected T-gain graph, then the largest eigenvalues of phi and W are equal if and only phi is balanced. Now some of the consequences of this result. Let phi W be a connected positively weighted T-gain graph, then psi W is balanced if and only if the largest eigenvalue of psi W and GW coincide. Let phi be, the next result says that let phi be a connected T-gain graph, then the spectral radii of phi and W coincide if and only if either phi is balanced or minus phi is balanced. So another is Channing spectral criteria that is also deduced from our previous result. Let psi be a connected sine graph, then the largest eigenvalues of psi and G coincide if and only if psi is balanced. Now we define a complete T-gain graph with respect to a distance matrix. Now, associated with a D max less phi, we can define a complete T-gain graph. So, a complete T-gain graph, this is a T-gain graph with vertex at V of G, and the gain of its edges with orientations from Vi to Vj is nothing but the phi max less Vi, Vj. And similarly, we can define KD mean less phi, associated with the minimum distance matrix with respect to less. Now, using this complete T-gain graph, we can give a characterization for balancedness. Let phi be a T-gain graph with vertex ordering less. Then phi is balanced if and only if KD max phi is balanced, if and only if KD mean phi is balanced, if and only if phi is distance compatible. Now another equivalent condition, let phi is balanced if and only if D max phi is co-spectral with the distance matrix of its underlying graph, D mean phi is co-spectral with the distance matrix of its underlying graph, if and only if the largest eigenvalue of D max phi and D of G are coincide, if and only if the largest eigenvalue of D max phi and D of G are equal. Let phi be a T-gain graph, then phi is balanced if and only if the distance matrix of phi exists and it is coincide with the distance matrix of its underlying graph. Now the characterizations of distance compatible gain graph. So first characterizations for bipartite graph. Let phi be any bipartite T-gain graph, then phi is distance compatible if and only if phi is balanced. Let phi be a T-gain graph, then phi is distance compatible if and only if every block of phi is distance compatible. Now the characterizations for distance compatible two connected T-gain graphs. So first we provide a lemma. Let phi be a two connected T-gain graph. And if S and T are two distance incompatible vertices with least distance, then there exist at least two internally disjoint shortest path from S to T which have different gains. Now using this lemma, we can characterize let phi be a two connected T-gain graph, then phi is distance incompatible if and only if there is an unbalanced event cycle, let's say C2n, such that there exist two diametrically opposite vertices S and T in C2n which have no other shortest path of length less than n. Now these are the references. And this is the paper where the result published. Thank you.
Any questions from the audience?
I think there are no questions from audience, ma'am.
Okay, Pooja. So thank you, Anirudh Saman, for the nice presentation. Next speaker is Kuldeep Sharma from Tejpur University. Title of the talk is Inverses of Non-Bipartite Unicyclic Graphs with a Unique Perfect Matching.
Hello everyone, my name is Kuldeep Sharma. I am from Tejpur University. So I will give a talk on the topic inverses of non-bipartite unicyclic graphs. So what is an adjacency matrix of a graph? The adjacency matrix of a graph Z is defined as the following matrix where the ijth entry is 1 if I is adjacent to j and 0 if they are not adjacent. And this is an example of a graph Z whose adjacency matrix is given like this. So what is a singular graph? We call a graph Z to be singular if AZ is a singular matrix, otherwise we call Z as non-singular graph. Now we came to the definition of perfect matching. A spanning subgraph H of a graph Z is called a spanning elementary subgraph if each component of H is either an edge or a cycle. A perfect matching is a spanning elementary subgraph whose components consist of only edges. For example, we can see in this figure that G1 has a perfect matching, namely the S set consists of V1, V2, V3, V6 and V4, V5, while G2 does not have any perfect matching. Now we find a formula for the determinant of a matrix. So this formula was given by Harare, and it gives the determinant of adjacency matrix of a graph in terms of spanning elementary subgraph of the graph Z. And if a graph has a unique perfect matching, then it is always non-singular. Now, what is an invertible graph? So first, this concept was given by Harare and Mink in their paper, which non-negative matrices are self-inverse. And according to them, a non-singular graph Z is said to be invertible if B equal to AZ inverse is a matrix which consists of only 0 and 1. And they give the following theorem, which says that a connected graph Z is invertible if and only if it is P2, the path graph on two vertex. So again, Gottschill gave another definition of inverse graph, which says that a non-singular graph Z is said to be invertible if the matrix S, A inverse S, is a non-negative matrix for some signature matrix S. Now, Gottschill first posed the problem of characterizing the bipartite graphs with a unique perfect matching that possesses an inverse. Now, these are some key work that has been done by many researchers. Now, what is the inverse graph? We give this definition by C+. We denote the graph on the same vertex set as that of Z that has been constructed as follows. Two distinct vertices I and J will be adjacent in Z+ if and only if alpha ij is non-zero, where alpha ij is the ij entry of the inverse matrix AZ inverse. So we call Z+ the inverse graph of G. So we use this terminology. By Pij we denote the set of all ij path P in G such that G minus Pp has a spanning elementary subgraph. Also, in a non-bipartite unicyclic graph with a unique perfect matching, cardinality of Pij is either 0 or 1 for any two vertex I and J. Now, what is an MM alternating path? A path E equal to U1 up to UK is said to be MM alternating if the edges on P are alternately matching and non-matching edges, with the first edge E1, E2 and the last edge UK minus 1 UK matching edges. So we give this formula which computes the increase of the ij entry alpha ij of the adjacency matrix of Q plus. So this is given like this. Now, adjacency in the inverse graph. So we proved that if U is a non-bipartite unicyclic graph, then I is adjacent to J in U plus if and only if U has an MM alternating path between the vertex I and J. So a mixed graph is a graph with different types of edges, say we red, orange and blue. And the adjacency matrix of a mixed graph is defined like this. So when the inverse graph is again a mixed graph, before we proceed, we shall need this definition which says that for a unicyclic graph U, a matching edge that is incident with exactly one vertex of the cycle is called a peg. In this example, the red colored edges denotes the matching edges and the edge 3, 4 is the peg. So when the inverse graph is again a mixed graph, and this theorem says that the inverse graph will be a mixed graph if and only if the graph U has at least 3 pegs. And this is the adjacency matrix of the inverse graph, and this theorem computes the entries of the inverse graph AU plus. Now, bipartiteness of the inverse graph. So what can we say about the bipartiteness of the inverse graph? And this lemma says that if U has R pegs, then the inverse graph contains a cycle of length R for R greater than equal to 3. And in particular for R equal to 1, U plus contains a triangle. And hence, this theorem says that the inverse graph will be always a non-bipartite graph. So what is a quasi-bipartite graph? A mixed graph is Z is said to be quasi-bipartite if there exists a partition of the vertex at phi Z like this, such that every edge between P1 P2 is undirected and every edge between P1 P2 is directed. And this is one example where you can see that the vertices, the sets P1, 1, 2, 3 and P2 forms a partition for the vertex at phi Z. While the undirected and directed edges are colored red and blue. So this theorem tells when the inverse graph is a quasi-bipartite graph. That is, U plus is a quasi-bipartite graph if and only if number of matching edges in gamma is given, where gamma is the unique cycle contained in U. Now we come to the definition of simple corona. The simple corona of a graph is a graph, another graph which can be obtained from the previous graph by adding a pendant vertex to every vertex of the graph. Here, the graph Z is the corona of H, because the graph Z can be obtained from H by adding a pendant vertex to all the vertices of H. So here we see that the inverse of U1 is a bicyclic graph, while in this figure we see that the inverse of U2 is again a unicyclic graph. So in this theorem, we answer that when the inverse graph is again a unicyclic graph. So this theorem gives necessary and sufficient conditions so that the inverse graph is again a unicyclic. So these three are the equivalent conditions. So now we construct two types of graphs. This is the type 1 that has been constructed in this way by taking a odd cycle gamma like this, P1, P2, Pn, and we perform the person 2. And for example, this graph is an example of a graph that can be constructed in this process. And similarly, we construct another class of graphs. We name this as type 2 graph that can be we construct in these 3 steps. And this is an example of a graph that can be constructed using these 3 steps. So, as we see previously that in this graph, the inverse of U1 is a bicyclic graph. So we try to characterize the graphs for which the inverse is again a bicyclic graph. And this is the theorem which says that the inverse is a bicyclic graph if and only if the graph U is either belongs to U1 or U2, where U1, U2 are the class of graphs that has been constructed in this type 1. This is type 1 graph which has been called as U1 is that class of graphs, while U2 is the type graphs that has been constructed in these 3 steps. So these are the results we obtained, and these are my references I have used. This talk.
Any questions?
Ma'am, there are no questions from the audience.
Okay, so we'll continue. Thank you, Kuldeep Sharma, for a nice presentation. Next speaker is Suman Maiti from NIT Roorkela. Title of the talk is Interval Eigenvalue Problems and its Applications.
Is a joint work with Professor Snehashish Chakraborty. By intervals, in practical situation when bounded errors appears, we can enclose them by compact intervals. This phenomenon influences us to study interval arithmetic. One can use narrow intervals for bounding errors in truncation of numbers, whereas wide intervals are used for path tracking of moving object in an uncertain environment. Preliminaries, interval arithmetic for two interval A and B, the addition, subtraction, multiplication and division are defined as follows. Provide in the division case, 0 does not belong to the interval. Image of a function under interval a variable are defined as follows. Now the image of a function under the interval variable may not be always an interval. So we need to compute interval hull, and this is the smallest interval containing the image of the function. Interval extension. An interval function is said to be an interval extension of a function if it is agrees at each point in Rn. Inclusion isotonicity. An interval function f is said to be inclusion isotonic if for every two boxes x and y in IRN with the property that one box lies in another, their image should be lies in one another accordingly. Fundamental theorem of interval analysis. If an interval function f from IRN to IR satisfies both the interval extension and inclusion isotonicity, then the image of an variable of an interval x under the image of f contained in the interval extension function, image of the interval extension function and of interval x. Gaps in the literature. There are eigenvalue bounds for complex interval matrices. We need to find more non-iterative formula for computing tighter bounds of eigenvalues. Aims and objective: finding new ways for computing tighter eigenvalue enclosure of complex interval matrices. Now we will define interval matrices. Now real interval matrices and real interval matrices is defined by a lower matrix A underline and a upper matrix A overline, and here inequalities are taken component wise. Symmetric interval matrix. Symmetric interval matrix corresponding to an interval matrix are defined is a collection of all symmetric matrices lie in an interval matrix bolded. Vertex matrices also defined matrices are defined also same way. Now the center, radius and absolute matrices of an interval matrix are defined as follows. Real interval eigenvalue problems. In 1991, they proposed this theorem for computing exact eigenvalue bounds of real symmetric interval matrices. One example here, we present one example which is shown as that one interval eigenvalue λ1 and another interval eigenvalue is λ2, and these bounds are exact for real symmetric interval matrix. Next, in 2005, Ron gave direct formula by the equation 1, which can enclose each eigenvalue of symmetric interval matrices separately. And another example we are given. Interval, now complex interval, we define complex interval matrices. Complex interval matrices is a order pair of two real interval matrices, and the center, radius and absolute matrix are defined in the similar way. Now the eigenvalue set of complex interval matrix is defined by the set capital lambda, bold capital, bold lambda. Now complex interval eigenvalue problem. In 1998, Ron proposed this formula for real and both real and imaginary part of an real interval matrix, which is involved by computing eigenvalues of the center matrix and radius matrices and the spectral radius of the radius matrices. In 2008, Harst proposed formula, similar kind of formula for complex interval matrices, which is given by the theorem. Now, in 2013, Ladik proposed another formula for both real and imaginary part of the eigenvalues of complex interval matrices, and which needs to calculate the eigenvalue bound for symmetric interval matrices. Now, we extend Gaussian-Disk theorem for complex interval matrices, and the bounds for real and imaginary part of the eigenvalues of the complex interval matrices are given by these two inequalities. Another similar kind of theorem for complex interval matrices are derived in this theorem. Now we will present an example. Here A and B are two real interval matrices, and by the Harst formula we can see that lambda belongs to minus 70.0752 up to 21.5727, and imaginary part mu of the eigenvalues lies in minus 16.8598 up to 17.3649. By the Ladik and Ron's formula, we have lambda lies in minus 14.0455 and 18.5467, and mu lies in minus 14.0497 up to 14.5374. By our present method, we can see that lambda belongs to union of three intervals and mu belongs to union of three intervals. And by the in this figure, we can see that our bound, which is blue, is tighter than Harst and Ladik. Now, we will discuss some application problem to stability. We consider a complex interval matrix where A and B are given as follows, and by the Harst formula we cannot conclude that it is truth stable or not, because the total bounds doesn't lie in the unit circle at origin. By the present formula, our formula, we can surely say that eigenvalues are lies inside the open unit disk at origin. That's why the matrix is truth stable. Now, if we consider a spring mass system with 4 degree of freedom, where stiffness and mass matrices are given as follows. By the different method Ron, Lang and He, and present method, we produce the bounds, and our bounds quite narrow, and this is tighter bound. One can do this diploma online related to interval problems. And one of our paper titled Gaussian-Disk theorem in complex interval matrices is accepted in the journal Proceeding of the Estonian Academy of Sciences. Acknowledgement: the first author is grateful to the Council of Scientific and Industrial Research (CSIR) for the financial support to perform this work. These are the major references. Thank you for listening.
Any questions?
Any questions from the audience? I think you can proceed, ma'am.
Okay. Thank you, Suman Maiti, for the nice presentation.
Thank you, ma'am.
Okay. Next speaker is Yogesh Kumar Prajapati from IISc Thiruvananthapuram. Title of the talk is Dynamics of Non-Negative Matrices.
In this talk, we hope to understand the dynamics of non-negative matrices, and this is a joint work with Sachindranath Jayaraman and Sri Hari Sridharan. We begin with the result due to Nussbaum et al. That A, B, and cross and non-negative matrix with spectral ADs at most one, then there exists a positive integer q, such that for every x with no, the sequence norm of a power k acting on x bounded. We have limit k going to infinity, a power kq acting on x equals to xi x, where xi x is a periodic point of a whose period divides q. This result talks about the periodic point of the non-negative matrix A, and this result is a consequence of classical parent-Frobenius theorem. A similar result is also there in literature for order-preserving subhomogeneous maps on polyhedral form. Let us recall the definition of periodic point. Let F be a self-map on a topological space X. An element X is called the periodic point of F if there exists a positive integer Q, such that F power Q of X equals to X, and such smallest integer Q are called period of the periodic point. The next result is due to three of us. Let A1, A2 up to A capital N be the finite collection of non-negative matrices, with each of them having spectral radius at most one. And this theorem assumes that a collection has non-trivial set of common eigenvectors, say E. Now, let omega be a finite bilettered word, and A omega with the matrix product associated with the word omega. If omega is given by omega 1, omega 2 up to omega p, then A omega will look like A omega p times A omega p minus 1 times up to A omega 1. That LCE denotes the set of all linear combinations of vectors in E intersection with Rn. Then for any x in LCE, there exists a positive integer q, such that limit k going to infinity A omega power kq acting on x equals to xi x, where xi x is a periodic point of A omega whose period divides q. Note that this integer q and the limiting point xi x are independent of choice of omegas and as well as its length. So now we work with LCE because we want to work with the set of all x with orbit being non-bounded property. So the hypothesis that each of the matrix has the spectral radius at most one, and the collection assumes a non-trivial set of common eigenvectors, say E, guarantees that there exists a non-empty set LCE for which the orbit is non-bounded for every x in LCE. And another reason is working with LCE is for a collection of non-negative matrices, or in general for a collection of matrices, it is very hard to find the spectral radius of the product of matrices. Motivation for this work comes from a discrete dynamical system, which I'll be stating in next slide. Again, we have a finite collection of matrices A1 to A capital N. We define the discrete dynamical system as we begin with a point x not in Rn, and we arrive at xj plus 1 by action of A omega j on xj, where omega j is chosen from the set 1 to capital N, and these omega j's are chosen randomly from the set. One remark here, if omega j equals to some constant c between 1 to capital N for all j, then the dynamical system coming out for specific choices of omega j is nothing but working with the theorem 1 due to Nussbaum et al. So Now, question is, can we generalize theorem due to Nussbaum et al. And the theorem mentioned previously in max algebra setting? And we hope to understand the dynamics of finite product matrices in max algebra setting. And motivation for working in max algebra setting, I'll be explaining in a few slides. For time being, let me explain what max algebras are. Max algebras are nothing but the examples of semi-ring. And I'll be stating some standard examples of max algebras. First example is the triplet R plus set of all non-negative real number with the binary operation circle plus. This is circle plus represents the maximization operation. The circle product is the usual multiplication. So this system is called the max product algebra. And another example is the triplet real set of all real numbers together with minus infinity. Circle plus, again here is the maximization operation. Here the circle product represents the addition operation. So this system is called the max plus algebra. Both systems are isomorphic to each other, but we prefer to work with the first one, the max product algebra. And whenever I say max algebra, I always mean max product algebra. Let me briefly explain the product of two matrices in max algebra. And that AB two non-negative real numbers, A circle plus B is maximum of AB, and A circle product B is AB. Now A and B are two n cross n non-negative matrices. They can be of different dimensions. It's just they have to be product compatible. That means that if we want to take product A circle product B, then the number of columns of A should be equal to number of rows of B. Then ith entry of A circle plus B is nothing but the maximum over A of Aik circle product Bkj. There is a natural relation between graphs and non-negative matrices. Let GA be the weighted directed graph of the matrix A. That is, GA has n vertices, namely 1, 2, small n, and there is an edge from the vertex I to vertex J if the ith entry of the matrix is positive, and we associate the weight Aij to that edge. Consider a circuit of length K, AI1, I2, I2, I3 up to Ik going back to I1 is the circuit of length K. Then the product AI1, I2, AI2, I3 up to Aik, I1 is the circuit product, and its kth root is the circuit geometric mean. And if we take maximum among all possible circuit geometric means in G of A, we denote that quantity by mu of A. This mu of A is nothing but the spectral radius in max algebra, which you can see in the next slide why this is the spectral radius. Before that, let me explain max eigenvalues and max eigenvectors. A is a non-negative matrix. That lambda is a max eigenvalue of A if there exists a non-zero non-negative vector x such that A circle product x equals to lambda circle product x. And this x is called max eigenvector associated to the max eigenvalue lambda. And the next result is due to Bipartitis. Let A be an n cross n non-negative irreducible matrix, then there exists a positive vector x such that A circle product x equals to mu of A circle product x. So this means here this mu of A plays the role of spectral radius. In other words, this is the parent root here and this is parent vector. So motivation for working with the max algebra is this result. This result can be considered as the generalization of classical parent Frobenius theorem, because it also applies on max algebra as well as to the usual Euclidean algebra. If we change the operation circle plus to addition and the circle product to multiplication, this result is also applicable in usual algebra. So as theorem 1 due to Nussbaum et al. Is a consequence of parent Frobenius theorem. So our idea is, can we get a consequence of parent Frobenius theorem in max algebra also? And one more remark here is, for an irreducible matrix A, there is only one max eigenvalues and one max eigenvector. And the next result is due to Elner et al. It says A be a non-negative irreducible matrix with mu of A equals to 1. Then A is a periodic matrix. What do you mean by periodic matrix? A is a periodic matrix if there exist positive integers Q and P naught, such that for all T bigger than T naught, we have A power T plus Q equals to A power T. And these powers are taken in Max algebra. A similar result on Boolean matrices is also there, and it is proved by Rosenblatt. And this is really important result, which I'll explain in next slide why this is important result. The theorem 7 can be considered as the consequence of the parent Frobenius theorem in Max algebra. Let A be a matrix with mu of A less than equals to 1, then there exists an integer Q, such that for every j between 1 and q, we have limit k going to infinity a power kq plus j equals to aj tilde, where aj tilde is a periodic matrix whose period divides q. Further, for every x in Rn plus, we have limit k going to infinity a power kq plus j equals acting on x equals to xi xj, where xi xj is a periodic point of the matrix A whose period divides q. Note that this period of xi xj is not equal to period of aj tilde. They can be different. Here, as in theorem 1, we find you can see that we had the limit k going to infinity a power kq acting on x, but here we get limit as operators, limit k going to infinity a power kq plus a equals to aj tilde. So for proving this theorem, the theorem due to Euler is really crucial. If it is irreducible matrix, then we can apply that theorem directly, and we get this kind of limit. And if A is not irreducible, then we use the Frobenius normal form, and the diagonal blocks are nothing but irreducible matrices in the Frobenius normal form. And we do some creative manipulations, and then we get this result to be true. So proof of this, I'll be giving some references toward the end. One can look for the proofs. So let us understand this theorem with the help of an example. Let A be given by 0.214, 1.56, 0.9. We find that the mu of A equals to 1 for the matrix A, and we also obtain that Q equals to 2 here. Then limit k going to infinity a power 2k plus 1 equals to a1 tilde, and limit k going to infinity a power 2k is a2 tilde. Period of a1 tilde is 2 and period of a1 tilde is 1. For any x in R3 plus, we also find that the limit k going to infinity a power 2k plus 1 acting on x is xi x1. Similarly, we can find the other limit k going to infinity a power 2k acting on x, xi x2. And the period for any non-zero x, period of xi x is 2. And this theorem is the generalization of theorem 3. So this theorem says let A1, A2, A capital N be collection of non-negative matrices with mu of AI less than equals to 1. For every I between 1 to capital N. Again, this theorem assumes that collection has non-trivial set of common eigenvectors, say E, say omega with the matrix product associated with the finite word omega. And for any x in LCE, here LCE is the set of all non-negative real linear combinations of vectors in E. We have limit k going to infinity a omega power k acting on x equals to xi x, where xi x is a fixed point for every matrix in the collection. I'll end this presentation with the help of an example which illustrates theorem 9, that A1 and A2 be two non-negative matrices. Observe that both the matrices are in Frobenius normal form. The matrices A1 and A2 exactly have two max common eigenvectors, namely U and B. For matrix A1, U corresponds to the max eigenvalue 1 and B corresponds to the max eigenvalue 0.9, and for matrix A2, U corresponds to the max eigenvalue 1 and B corresponds to the max eigenvalue 1. Now, if omega is a p-letter word which has presence of both letters, then for any x in LCE, an x will have this form, which is alpha u circle plus beta v, where alpha and beta are non-negative real numbers. Then the limit k going to infinity, a omega power k acting on x equals to xi x, where xi x turn out to be alpha u. And we find that xi x is the common fixed point for A1 and A2. The proof of the theorem 3 and 7 and 9 can be found in these two, and both are in archive. Thank you.
Any questions?
Any questions from the audience? I think we can conclude the session, ma'am.
Okay. Thank you, Yogesh Kumar Prajapati, for the nice presentation. It was the last presentation of this session.
Yes,
Thank you, one and all.
thank you so much, ma'am, for chairing the session. Thank you, speakers, for your wonderful talk. So we will have a lunch break from now 12:30 to 1:30 IST, and the next sessions will start from 1:30 IST.